Today we are going to do section 5.3 on page 439. So what are we doing? Graphs of polynomial functions. The polynomial functions look more or less the same. Okay, so let's look at example 1 to see some of the examples of what they look like. And the first one, that is some polynomial. It points down, so it's some kind of even-powered polynomial, and maybe the highest power is 4 or something like that. And then so that is a polynomial. The example that over there that look like a V shape, that is definitely not a polynomial, because a polynomial doesn't have sharp corners. That thing is probably some kind of absolute value function, because absolute value functions look like V's. Okay. Now so let's continue looking at this thing. That is most likely a polynomial of some odd power, because the even-powered stuff, they all end up pointing the same direction. Whereas the odd power ones will point at one direction, the other side point at the opposite direction. And then the fourth thing would have been a polynomial if it wasn't broken. Okay, it's missing a part, and that's the only reason it wouldn't be a polynomial. Although the unbroken part might be a polynomial anyway. So that's example 1. F and G are not, they're not polynomial. The last one isn't polynomial only because it isn't continuous, as the book says. So next, let's look at example 2, where we are going to do some factoring. All right, the factoring trick is identical to what we've been doing in factoring. So please do this example yourself. Although I probably am not going to write it down. The example is here. Okay, let's look at this for a second. We have x to the power 6, and the lowest power is x to the power 2. So let's factor the x to the power 2 out. Anytime you see a common factor, the first thing you do is take it out and put it on the side. Okay, I don't mean throw it away. Just put it on the side, so then you have that stuff left. Which that thing is still not, it's not a quadratic equation, but it looks like one if you pretend that x squared is a variable. That is, pretend that x squared is u, or x squared is just one thing. Okay, then if you pretend it that way, then x to the power 4 is like x squared and then squared again. And treating it like a quadratic function that way, then you can factor it. It becomes x squared. With the regular factoring trick of factoring a quadratic equation or whatever. So then you're able to come up with various factors. Now let's see. Right. So here you have 3 situations. First, x squared is 0, okay, which gives you x is 0. Next, x squared is equal to 1. And then that gives you x equal to positive or negative 1. And thirdly, x squared equals to 2, which gives you x equal to positive or negative square root of 2. And so with that, you have that this polynomial has the power of 6, so it has 6 roots. And the 6 roots consist of 0 is being repeated, and then 1 and minus 1, and then square root of 2 and minus square root of 2. So if you are to plot this thing, it will look like this. Look like this thing itself. Now please plot this graph yourself. Okay, maybe not this one. Maybe, but well, yeah, let's skip this one. But anyway, the book has plotted it, and as you can see, this is a standard even polynomial, x to the power 6, and then it has it has 1, 2, and then 3, 4. It has 2 zeros doubled up at origin at 0, 0. And then 5, 6. So all 6 roots are accounted for. Okay, that is all 6 x-intercepts. Now, let's see. Right. Another thing I want to mention is anytime you have a double root like that, then the graph will touch instead of cut across, it will touch the graph, the x-axis. See, in other words, it joins it smoothly instead of cutting clear across. So that that happens when you have double or more roots at the exact same place. Like in this case, x is 0 twice at the origin. and therefore you see it just barely come in a smooth touch situation instead of just cut right across. So you smoothly touch it and then they come right back up. So that's that. And then let's look at example 3. So please do the factoring in example 2 as part of your homework. Is we've already done that in the past several times, but it's good practice to do the factoring again. So next, let's look at example 3, where we have another thing of factoring going on. Okay, we have a polynomial, and let's factor it and hope that and be able to see where the roots are or where the x-intercepts are. They are basically the same thing. Now, the factoring is done here is identical to what we've already done in the past. What happens is that we'll group these things together. The first two group together and the second two group together. Why? It's just something we try and hope that it works out. And it does, because once we group it together, you realize that there's a common factor, x minus 5, showing up in the two groups. And that doesn't always happen. Okay, and we will see in the next example when it doesn't happen. But in this case, we are having good luck and it does work out. So we group it this way, the first step, and then we pull out the entire x minus 5 as a common factor, and which gets us to here. There will be what's left is x squared minus 1. Okay, because the other thing has nothing but 1 left. So then we have, and then factor the square. That's a perfect, that's a difference of squares, which becomes the plus and minus version. And then we have a bunch of, from there we have 3 roots that come out, and which give us the graph of something that look like this. Okay, that's a standard x to the 3rd power graph where it goes up and down and up. It has 3 distinct real roots. So everything's pretty standard. And being that the leading coefficient is positive 1, okay, that is the number in front of x cubed is positive 1. So this thing goes to positive infinity as x goes to positive infinity, and goes to negative infinity as x itself goes to negative infinity on this side. So that is very standard x to the power 3 3rd degree polynomial. So please do that yourself as well. Next, let's look at example 4. Okay, example 4 is simpler yet. It already did the factoring for you, so we'll repeat that process and then plot this thing. I want to mention that in this example, being that it was it has a repeated 0 right here. Okay, so whenever there's a repeated 0, the graph will barely touch it. In this case, it barely touched it, and then it turned around and went back where it came from. So it went down and then back up again after barely touching the x-axis. So that indicates there's a double root here. And then there's another root that is just on the other side. And that is right. And you can see that by looking at the polynomial itself. See, it says that the polynomial, once factored, is x minus 2 to the power 2. That means it has a double root at x equal to 2. Which is, and whenever it has a double root, it will barely touch it. But it doesn't necessarily bounce back though. Sometimes it barely touch it, but then it then continue to go in the same direction after it turned. And we'll see that in a moment, I'm sure. Next, let's look at example 5. And now this thing, we're not going to be doing any factoring. You can try, and I suggest that you do. Okay, try to factor. And very soon you'll realize that factoring it will get you nowhere fast. Somehow it just doesn't factor. So how do you find the root of this thing? Well, you're going to do some various other tricks. One of them is try various numbers, say 1. You try factors of 6. Okay, we're not gonna go into that right now. This was taught. This might be taught at some other time. But what happens is that you try different plug-in. You do a trial and error. You plug in, say, x equal to 1, and see if it works. In this case, if you plug in x equal to 1, it does work. Okay, because 1 plus 4 plus 1 minus 6 is 0. So x equal to 1 actually works. And then you do something called long division. But we're not going to do that right now. We're just going to realize that the regular factoring is not going to get you anywhere. So what are we going to do? Well, we're going to plot it out on the Desmos graphics calculator. Okay, and if you do, you come up with something like this, and the calculator will tell you where the roots are. The roots are at 1. We already figured that out just by trial and error. And then there are 2 other roots at these 2 other values of -2 and -3. Now, so the calculator will tell us where the roots are, but these roots happen to be pretty nice in the terms that they're all integers and stuff. But there's no guarantee that that's going to be true. Okay, sometimes the roots might have a square root in it or whatever, as we have seen in a few examples ago. And that the root, I think, was a square root of 2 or something. That's totally possible. Anyway. So that is the graph of this thing. So please plot this graph on the Desmos calculator. I have it plotted here myself to show you. So here's what I typed out on the thing. I guess that's it. No? Okay. Okay. So let me show you what this looks like on the Desmos calculator. Okay. I have the whole entire screen, a screenshot, including the web page, and what you do is type it in exactly like this. Okay. To type in the power x to the power 3, you will put shift 6, as I have mentioned before. And then and the other symbols are the same. And then after you type in the 3, you need to push the down arrow or move the cursor down or something to get it out of the power position. So please do this, okay, and make sure you can get it. If my explanation isn't good enough, you still can't get it to work, then please look at Desmos explanations. They have tutorials, or look on YouTube or something. They are online. Other teachers or whoever that will show you exactly how to use the Desmos calculator. And you must learn how to do this, okay? There is no reason that you should say, I tried but couldn't get a Desmos to work. That is not acceptable. Please try to do your very best to get this to happen. It shouldn't be a problem, but you know, if it is, you do not give up, okay? If it is a problem, you need to pound it through until it isn't a problem anymore. So that's that. So next. And of course, if for some reason you simply don't have access to the Desmos calculator, then it's okay. Okay, don't worry about it. I didn't have Desmos calculator or any graphics calculator when in my day of studying this stuff, and I turned out just fine. So you don't have to. And you might ask, so how did you graph this stuff back in your day? Did I just plot it out the hard way? No, I believe I just skipped it. But anyway, let's move on. Now let's get to page 444. Okay, here is a function, and we're going to talk about the multiplicity of zeros. What that means is if you have more, look at this function right here. We have, x equal to -3. Okay, that is 1, 0. X equal to +2. But that is there twice. See, you notice to the power 2, that means is x equal to 2 twice. And then x equal to -1 3 times. So when x equal to 0 twice, you notice what happens. It bounced back. And then when x equal to -3 and -1, you notice that it touched it, but then it continued to cross, okay? It didn't bounce back. It continued to go down, but it touched it first. That is, it joined the x-axis briefly, just for 1 second, or 1 moment when it reached that value, -1, and then it just immediately turned and continued to go down. Okay, it didn't bounce back. That's the third power. So in general, what happens is that for even powers, that is, if x minus 2 is being multiplied by 2 times, 4 times, 6 times, then the graph will bounce back and do that trick. Whereas if it's raised to the odd power, but more than 1, okay, if it's just 1, it just crosses it. But if it raised more than 1, but in an odd power, like in this case, x has 3 roots equal to -1, then you will touch it, and then it just you come to a smooth point, and then immediately keep going down. And that is There's a name to this thing called multiplicity that is not particularly exciting, but it's there, so I'll mention it. Generally speaking, the multiplicity is when it equals to 1, you just cross over, okay? When it's 2 or some other even number, that is your roots are there, like x equal to 2, in this case is at 0. But if it's at 0 equals to the root is repeated in an even number of times, it bounces back like that. And if the root is repeated with odd number of times, then it'll touch it like this, and then it just sinks. It continues going to the other side. Okay, so it crosses it, but in a touching way, like that. Instead of when it's not, if it's just a single 0, then it crosses it just cut right across. There's no touching or nothing. Just dive straight down or up. So that is that. And so that is the point of example 6. Please, on the following page, 445, please do that example as part of your homework. It explained exactly what I said before. Okay, so please read that yourself and figure it out. So example, next, let's flip the page. And finally, example 7, the turning point. Yeah, well, the turning point, as we have mentioned before, for any, I'm now on page 448. So on page 448, we're talking about turning points. The turning points, as it says here, a polynomial has at the most, if it has degree n, it will have at most 1 less of n turning points. That you have n minus 1 turning points. So yeah, it's just a fact that these things are turning points that we mentioned in the previous section. So it just means that it might turn, or it might have far less than n minus 1 turning point, but yeah, it might have 0 turning point. Okay, because how can it have 0 turning point? Well, sometimes a polynomial might look like this. Like for example, y equal to x. Okay, that's just a straight line that goes down, or any other straight line for that matter. It has no turning point whatsoever, right? And that's not only the straight line has no turning point. You can have this thing, well, that looks too straight. Let me draw another one. Okay, that is like, well, yeah, like that. It has no turning point either. It doesn't. It just cuts. Is that possible? That is, well, whatever. The point is, well, I know that at least the straight lines don't have turning points, right? The rest, let's not worry too much about it and worry our brain thinking too much about this type of thing. And so please look at example 7 yourself, okay? Anyway, so let's look at the next part, example 8. How do you sketch a polynomial function? This was done back in the good old days when there was no Desmos graphics calculator or TI-84 or any such thing. And so what we're gonna, so that was how things were done. Nowadays, we're gonna graph it by typing quickly in the graphics calculator. But what the book is trying to tell you is, what if you have no graphics calculator? Then you just gather up all the information you can. That is, you factor this thing, you figure out where the zeros are, okay? And then you figure out what does it do at the end, and whether the zeros are multiplicity, that is, do they just touch it, or do they cut right across? And how do they touch it? Do they bounce back in the terms of even number of zeros, or do they go touch it and then keep going again? Odd number of zeros, either way. So with that kind of information, then you can graph this thing and draw a fairly decent graph of doing it. So this was done back in the day when there was no graphics calculator. In other words, my days, okay, back in my day. So is that what I did? Yeah, I doubt that. I think I just skipped it or avoided it or something. I'm lazy. I don't want to do this kind of grunt work. So let's flip the page to 451. Yeah, and look at the intermediate value theorem a little bit. So the point I say is that I should mention that that you should know how to do this, okay? It doesn't mean you have to do it, because I sure didn't want to do it. It's a graphing for polynomial is like there's much more fun thing to do in math or in life for that matter. So anyway, using the intermediate value theorem, first let's talk about what it is. The intermediate value theorem on the bottom of page 451 basically says that if you have a river, here's a river. Excuse me. If you have a river and there's a guy, okay, a guy was here. Here's our guy, and then at some other time later, you notice that the guy is here. What does that mean? Remember, this is my river, and the river goes both directions indefinitely. Okay, so what happened? The guy was here, and then he got to the other side of the river. What does that mean? The intermediate value theorem says if that is the case, then the guy crossed the river at some point. That is the intermediate value theorem. Okay, it must have hit the river. It hit the river at some point, and then it was able to continue going. So that's the point. And to put it in the math value is let's read this line. It says that let f be a polynomial function. The intermediate value theorem states that if f of a here, okay, and f of b have opposite signs, that is, this is the x-axis, f of a is down here, and f b is up there. It crossed the river, the function did. Then there exists at least one value c between a and b where f of c equal to 0. That is, at one point where it did cross the function crossed the river, where its value is 0. Because the river is the x-axis, it has to be 0 to cross the river. All right. Now, the intermediate value theorem, you might think, I think that's pretty obvious. Okay, why do you need a theorem to say something that obvious? Well, the truth about the intermediate theorem is that while it might be obvious, it is proved in advanced math. So if you want to learn how to prove the intermediate value theorem, then please finish this algebra class. Then you take trigonometry, pre-calculus, then calculus 1, 2, 3. And after you finish all that, then you can take a class that will prove the intermediate value theorem to be true. Now, until then, let's just pretend that it's true and pretend that it's obvious, and anybody who doesn't think so is nuts or something. So that is the intermediate value theorem. And with that, let's look at example 9 on the next page, where it says we have a function, right? And we can show that when x equal to 1, the function is, I don't know, what is x equal to 1? And then x equal to 4. And now let me see. Let me check. All right, so the question is, the function thinks that there should be let me see. All right, so that's fine. So we have a function, right? And then what you're supposed to do is you need to show that there are two zeros. You don't have to find them necessarily. You just have to show they're there between 1 and 4. So what are we gonna do is calculate certain values, okay? That is, say there's the function, so we calculate certain values. First we calculate what is f of 1, which turns out to be 5, I guess. Yeah, anyway, so then we calculate f of 4, which I'll just trust that it'll end up being 2. So you have 5 and 2, and they're both positive, so you're not going to apply the intermediate value theorem. We need something negative, okay? Because the intermediate value theorem says if you have something negative and something positive, then something has to be 0 in between. The river has to be crossed, but only if you're on different sides, right? If you're both on the same side, that'll tell you zip. So let's try something else. So we'll calculate something f of 3. Now f of 3, then you notice that it does end up being a negative number. So at that point we are done, because so it says that we have to show there has to be 2 real zeros. So f of 1 is positive, okay? We show that that's f of 1. Yeah, f of 1 is positive. F of 4 is also positive, is over here. but f of 3, which is in between them, f of 3 is down here, is negative. That means that we have this guy cross the river at least twice, because he got back, you see. That's why, so applying the intermediate theorem here and then here, that means we have at least, the guy crossed the river twice, or put in a math way, is that we have two, it at least has 2 zeros. I mean, he might, you say, well, what does at least mean? Well, he could have been crossing it a zillion times here. It doesn't say it didn't, right? We can't prove that he didn't. All we know is that he crossed at least once. Yeah, well, anyway, so I'm just saying. So we proved that by intermediate theorem that he crossed it one time. So that's that. And next we have, given a graph, we need to write a formula for the function. Okay, so let's look at example 10 on page 453. So we are given the graph of some polynomial, and we need to write down the equation for this thing just by looking at it. So that takes a bit of a guess or estimation, but we'll do the best we can. First, we notice where the x-intercepts, that is, where are the zeros. The zeros are at -3, and then 2, at least twice, right? And then 5. All right, so we'll write that down. The polynomial will be equal to x, let's see, x plus 3, okay? X plus 3. X plus 3 means it has a 0 at -3. And then times x minus 2. X minus 2 means it has a 0 at +2 twice, at least. Twice. And then x plus 5. It means, x minus 5 means that it has a 0 at +5, at least, well, this case is just one time. And so judging by that, you might say, well, how do I know this isn't the 4th power? Because any even power do, but we'll just guess the least amount of power, okay? Because we don't want to wear ourselves out. So the least amount of power it has is probably the 2nd power. It's going to be the 2nd power because it bounced back. Anytime it touches the graph and bounces back, that means it has an even power. So we'll pick the least one because, make life easier to us. However, we don't know what these are just the zeros. We still don't know what the coefficient is, okay? There could be some number here. I mean, this number might not be 1, and whatever number is here, then this polynomial still have the same zeros, right? However, this number can be determined by the y-intercept. So let's look at the y-intercept. Well, the y-intercept says that when x is 0, y equals to -2. So this graph has to fit this equation. So when x is 0, y had better be -2, okay? Now with that information, we can plug x equal to 0 in here and calculate what a is. So this is our polynomial. And with that, let's calculate it, okay? So let's calculate f of a, because, f of 0. Because once we plug in f of 0, the polynomial has to fit that equation. F of 0, it had better be equal to a times plug x equal to 0 for all of these things. So we have 3 times -2 squared times -5, just -5. So that means f of 0 equal to, f of 0 equals to -2, right? So that equals to -2, and what is that? That's 3 times 4 is 12. 12 times 5 is 60, and that's -60, which means a is 1/30. If I'm not mistaken, let me check against the book. Yep, a is 1/30. Okay, I got the sign right. Therefore, if you plug a into its position right here, then f of x equal to 1/30 times all the stuff. That is the polynomial that we graphed. Yeah, okay. Well, anyway, so that's example 10. Please do this yourself as part of your homework, just to, get used to doing this type of thing. Just have an idea is how important is it to look at a graph and know what the polynomial is. not that much maybe, but it's good. It's still standard knowledge for algebra. So if you do it once or twice, that should be sufficient. And yeah, so next, let's go to the next page. We're considering the local max or the global max. Okay, what page is this? This is 454. So please go to page 454 and let's look at the graph there for a second. Okay, there is a quick graph that shows you all the maximums. Now, there are two humps there, okay, two mountain peaks. One is called the local maximum, and the other one is called global maximum for obvious reasons. Okay, the global maximum is the absolute highest point this function can ever get. From negative infinity to positive infinity. The local maximum is just a local high point, okay? It's local because everything around it is lower than it, the highest point. But if you look any farther, there are people far away that's taller, but if you just look at this immediate area, all the way around, on both sides, everybody is lower. So it's a local hero, okay, a local max. So, which is fine. And similarly, the one down here is a local minimum in the sense that in this immediate area, is the lowest point. But if you look farther, of course, the graph eventually goes lower than it. But if you don't look too far, then it is the lowest point of the graph. All right, so next let's look at the next example. Okay, this is a standard problem, example 11, where you got a box. You're gonna make a box, and how are you gonna make the box? By cutting out 4 corners and then folding it up. Okay, and well, anyway, if you have a hard time imagining what that means, just cut this thing out. Get a piece of paper and cut it out, and then fold it up, and you'll be cut out all 4 corners and throw it away. Okay, 4 corners are all squares, so they have to be identical squares. So once you cut that out and fold it up, it'll turn into that box we're talking about. So what are we doing? There's a box. Each corner, and it has a dimension. The paper does. Okay, it starts out as 14 by 20. And then we need to figure out the way to cut this thing so that your box has a maximum volume. All right, so let's do that. So here's our box, okay, that I drew it out. And the thing has a dimension of 14 here by 20. Right. So which means that when you're done cutting, the box that you created, the length will be 20 minus 2w, because the corner got cut out, 2w. Okay, and the height will be w, and the width will be 14 minus 2w. See, that's the box. Once you cut the corners out, throw it away, and then fold all 4 sides up into this thing. Okay, so then, so what is the volume of this thing? The volume of any box, okay, is length times width times height, which is that thing. Let's start with length, 20 minus 2w, that's a 2, and then times 14 minus 2w, and then times w. All right. So that is the entire volume of this thing. And once we have the volume out, then so then you notice how many w. This is a polynomial, but what kind? You have w, w, w. So it's the third power. Okay, some kind of a third power polynomial. And then we're going to graph this thing on the decimals calculator or something. Yeah. And why? Because we're trying to figure out what the maximum is. And so if you graph it, then so please graph this thing on the decimals calculator, and then and if you can. So then we have but let's look at the graph in the book. Okay, in the book you notice that once you plot it in, by the way, in the decimals calculator, you don't have to multiply it out. You can type the graph exactly as is by typing in the parentheses, okay? But I don't think you can use W. I think you have to use X. if you were to type it in. But anyway, just change the W to X, then you're good. So type in this stuff, including the parentheses, and then that should come out, and then you should get a graph that looks exactly like this thing. And the next step is we need the maximum, because we're looking for the maximum volume. So you look at the graph. Where is the maximum? It's about W equal to somewhere between 2 and 4, okay, as a maximum. Of course, you say, well, but if W is way over here equal to 12, then you'd be even higher. But W cannot be 12. I mean, this whole thing is only 14, okay? W cannot be more than 7, which is half of this. In fact, it can't even be 7. If W is 7, then your box is odd. Yes, your box will have no width, which makes no sense. So W had better be less than 7, which just by intuitively, you can judge that W is probably around 2 or something. I don't know. Anyway, so judging from this graph, W is somewhere between 2 and 4. Hard to say. 2, maybe, it looks to me like it's less than 3. Okay. But on the decimal calculator, you can click on the top, and it will give you exactly what the coordinate is, the x value. So then okay, it's about, in the book it says it's about 2.75. Okay, and if x is 2.75, the y value is somewhere about you see, the y value is about I don't know, maybe 300, and if you eyeball it, it's about 340, and that is good enough. Okay, which is also what the book says, is roughly. But if you click on the decimals calculator, it will tell you the exact value. It might be 340 or not, and doesn't matter, okay? The calculator is very smart and will tell you exactly what it is. But that is how we set up the problem. Once you set up the problem, then you can type it into the calculator and know the exact solution. But you might wonder, but how would I do this if I didn't have a calculator? Then you just graph it by hand and estimate it the same way. You know, you can do that too. It's not like the calculator is the only way who knows how to graph this thing. But doing it by hand, of course, is a real pain, and I'd rather not do that. So having said that, we have come to the end of this section. And for homework, on page 457, I guess, okay? Please do problems 17, 21, 27, 33, 47, 51, 55, 61, 71, 73, and 79. And they're all really straightforward problems. Most of them are pretty short, so I won't be going over them. So please do that yourself, and then let's move on to the next section.